Okay, so thanks for staying around to the last talk on the last day. And this was rescheduled from this morning because I missed a flight from Hong Kong. So I'm going to be talking about an optimal algorithm for finding heavy hitters. This is based on a few papers, joint work with Vladimir Braverman, Stephen Chestnut, Nikita Ivkin, Jelani Nelson, and Jungyu Wang. Okay, so let me first define the streaming model for the purposes of this talk. We see a stream of elements, A1 through AM. So M is the length of the stream. And each element is an integer between 1 and n. And for the purposes of this talk, the length of the stream M is assumed to be polynomially related to n. The elements are presented in an arbitrary order. And algorithms are given one pass over the data. And we'd like to, among other things, minimize the memory usage or the space complexity in bits for solving a particular task. What we're going to be looking at are functions of the frequencies or number of occurrences of an item. So let f sub j be the number of occurrences of item j in the stream. Our goal is to solve the heavy hitters problem, which is to find those items j for which the frequency f sub j is large. And I'll define a few notions of largeness on the next slide. Okay? So what does it mean for frequency to be large? One guarantee is the so-called L1 guarantee. And here, what you'd like to do is to output a set of items containing all those items j whose frequency f sub j is at least phi times m, where phi is an input parameter. You can think of phi as being like 0.1. Okay, so all items that occur at least 10% fraction of the stream. And the set should not contain any item j whose frequency is at most phi minus epsilon times m, where epsilon is also a parameter. You can think of epsilon as maybe being phi over 2. The reason for the introduction of epsilon is because if epsilon is 0, then this is actually a very hard problem. Okay, finding things that are exactly above a threshold requires actually linear space. So that's the L1 guarantee. Now there's what's called the L2 guarantee, which I'll argue is stronger. So here, define capital F sub 2 to be the sum of squares of the frequencies of items. Okay? And analogously to the L1 guarantee, we would like to output a set of items containing all those items j whose squared frequency is at least phi times f2. Okay? Those items whose squared frequency is at least a 10% fraction of the overall sum of squares of frequencies. And we also don't want to output any item whose squared frequency is at most phi minus epsilon times f2. And for those items in between phi and phi minus epsilon, we can do whatever we want. So I claim the L2 guarantee is much stronger than the L1 guarantee. So in this talk, we're going to think of phi and epsilon as being constants. Okay, fixed constants independent of n. And here's an example of a frequency distribution on items where the first item is an L2 heavy hitter, but is not an L1 heavy hitter. Okay, so suppose the first item has frequency root n, and all the other items have frequency 1. Then the sum of all the frequencies is theta n. Okay, you have n items, so it's n plus root n. And the first item only occurs root n times. So to find it with the L1 guarantee, I would need to set phi to be roughly 1 over root n. It's not an L1 heavy hitter for constant phi and epsilon. On the other hand, item 1 is an L2 heavy hitter. Why? Because if I take the sum of squares of frequencies, this squared is n, each of these squared is 1, I still get theta n as being f2. But the first item's squared frequency is n, so it's a constant fraction of the overall f2 value. Okay? In general, an algorithm that achieves the L2 guarantee for constant phi and epsilon also achieves the L1 guarantee. Okay. So what is known about achieving the L2 guarantee, which will be the focus guarantee for this talk?
Actually, there's something I don't understand about your previous claim.
Okay.
If the algorithm outputs the first element, why does that achieve the L1 guarantee? The set will contain an item that doesn't satisfy the second property. Right?
Yeah, so this does not satisfy the L1 guarantee, right? If I set this phi and epsilon to be constants, and I ask you, please solve the L1 guarantee on this vector, then you will not return the first item.
I see. So maybe I misunderstood what you were saying. I thought you were saying that an L2 algorithm is also an L1 algorithm.
Oh, I didn't explain why that is. I'm just saying that, yeah. I mean, so you do have to test to not output false positives. But I'm just saying, for this vector, it will be returned by an L2 algorithm, and it won't be returned by an L1 algorithm. Okay, I won't, yeah.
If there are L1 heavy hitters,
Yeah.
then are there any L2 heavy hitters also in there that are not L1 heavy hitters? Or do L1 heavy hitters like wash out all the L2 heavy hitters?
Okay, so if I'm at least a phi fraction times the sum of the frequencies, then my squared frequency is at least phi squared times the sum of squared sum of frequencies. The squared sum of frequencies is at least the sum of squares of frequencies. Okay, so that means I'm at least, I'm also an L2 heavy hitter with phi squared, say. Yeah. So if I'm an L1 heavy hitter, is that your question?
Yeah, so think in that case, like there are going to be nothing on the order of square root of n will show up at all in the first.
You're asking the converse. So you're saying if I'm an L2 heavy hitter.
So in the presence of an L1 heavy hitter, there won't be something that's an L2 heavy hitter but not an L1.
Yes, that's my question.
Oh, in the presence of an L1 heavy hitter, there won't be something that's an just because. Yeah. The single L1 heavy hitter sort of dominates the sum of squares. Yeah.
Wash everyone else out.
Yeah.
And the algorithm will find that one.
Yeah, we'll find that one. Yeah. Okay. So let me explain like the previous best algorithm for solving the L2 guarantee. This is due to Charikar, Chen, and Frock-Colton. So assign each coordinate or item, as I've been calling it, I, a random sign, sigma I. Okay, probably 1/2 1, probably 1/2 -1. And what we do is we're going to randomly partition the items into B buckets. Okay, I've drawn a picture here. And in each bucket, we're going to maintain a counter. Okay, so what we're going to do is we're going to, for each item, I've written it as a list of frequencies. Each item gets hashed to some bucket. Okay, so there's a hash function h. And this is the second bucket. And for instance, this item number 4 goes here, so h of 4 equals 2. This is the set of items that go to this bucket. And what we maintain in that bucket is the sum over all items there of their frequency scaled by their sign. Okay? So this can be maintained in a stream because if I see a new update to, say, item 4, I look at which bucket it hashes to, I read its sign, and I just add its sign to what's already there. Okay? I should also mention that these signs don't need to be truly independent. You don't need a list of n random bits for these signs. They can be generated pairwise independently. So log n bits suffices. And for this hash function as well, it doesn't need to be truly random. Pairwise independence again suffices. So log n bits for the randomness. Okay, so what do we do with this data structure? I claim you can estimate the frequency of any individual item I. And I can get an unbiased estimator. So I estimate the frequency of item I as follows. I look at the bucket it hashes to, h of I. I look at the counter in that bucket, c sub h of I. And I multiply by its sign, sigma I. Okay? I mean, it's a lot of items are getting the same estimator, right? Any items that go to the same bucket and have the same sign are estimated the same way. And so what? I didn't say it has low variance yet. I just said it's an unbiased estimator. Okay. So why is it unbiased? Let's look at the expected value of the estimator. Okay. And in fact, this is just, I just need to take the expectation over the sine function for any fixing of h. So this is equal to sigma I, so there should be an expectation everywhere, sigma I times the sum over all other items I prime that hash to the same bucket as I of sigma I prime times frequency I prime. Okay? Okay, I didn't write it. The point is though, when I take the expectation of sigma I times sigma I prime, if I does not equal I prime, this expectation is actually 0. Right, here's pairwise independence. That's all we needed. On the other hand, if I equals I prime, then sigma I squared is 1. And so the expectation of this quantity is just the thing multiplying sigma I, which is f sub I, the frequency of item I. Okay, so I'll explain in a second what kind of concentration around the expectation you get. But let me say the algorithm. So you're going to repeat this basic hashing scheme order log n times independently. Okay, so you hash into capital B buckets. And think of capital B as being a constant. Okay, it's some function of phi and epsilon, these parameters to the problem that we said were constant. You hash to a constant number of buckets, and you repeat that independently log n times.
When you say you repeat it, you mean you have parallel copies?
Parallel copies, yeah. Okay, so actually in particular, the space is going to blow up by log n factor. Okay. What you're going to do to estimate, I just want to estimate some item's frequency. What do? I look at one of those parallel copies. I look at this estimator. You know, it's an estimator of its frequency. I evaluate it. And then I do that for each of the log n copies. And I take the median of all the estimators. And that's my guess for what the frequency of item I is. Let me just make a comment on how concentrated this is around its expectation. Okay, let me say this bullet first. So the noise in a bucket, meaning, so when I compute sigma I times the counter in hash bucket I legitimately get f sub I plus something else. Okay, and that something else had expectation 0. That something else was sigma of I times the sum over all items I prime not equal to I, which hash to the same bucket as I, of sigma I prime times their frequency. We said it's expectation 0. But what does it look like? Well, if I take any vector, any fixed vector, and I take the inner product with a sign vector, then what does that quantity look like? So that concentrates to the Euclidean norm of the fixed vector. Okay? So what does that mean? Well, now we have to actually use the randomness in H. Okay, so far all we've been saying is all this holds for any H. Well, what is the expected squared Euclidean norm of all the other junk that goes to the same bucket as a given item? Well, I take the sum of squares of all frequencies. That's this quantity f2 we looked at. And I have capital B buckets. So I expect about capital F2 over B sum of squares junk inside that bucket. And when I take the inner product with a sign vector, I get concentration to the square root of that. Okay, so that's the additive noise in your estimator for a given one of these log n repetitions. That's the additive noise with constant probability. And by repeating this log n times in parallel and taking the median, I can ensure simultaneously for every item I that its frequency is approximated up to this additive noise. Right? With probably 9/10 it's approximated up to that for one of the copies. And there are only n items, so log n independent trials. Okay, so we said the number of buckets was constant. It's roughly some function of phi and epsilon. Now, what is the space complexity of this? Well, I have to maintain a counter in each of these constant number of buckets. That's log n bits. Right? I mean, it's sum of frequencies. It's some integer between, poly n magnitude, log n bits. And I repeat the scheme log n times. That gives me log squared n bits of space.
So the log n repetitions You're saying they don't reduce the identity noise in any one frequency, but it's just to get a uniform bound across all.
Yeah. So let me emphasize that because I didn't so far. So why are we doing this? Well, we want to approximate every single frequency up to this uniform bound, because if we can do that, then we can figure out which ones are the heavy hitters and which ones are not. Right. So recall we want to find all those items whose squared frequency is at least, say, phi times f2. Right? So if this is the additive error, sort of the squared additive error, think of it as being without the square root. It's roughly f2 over b. So if b is something like 1 over phi, then this will give me everything which is additive error phi times f2. Okay? We actually want additive error epsilon f2. I don't know if you've been paying attention to all those details, but we want additive error epsilon f2 so we don't misclassify items. But anyway, it's a constant, right? So b is like 1 over epsilon. Yeah. So if every item is approximated up to this additive error, we can figure out which ones are heavy and which ones are not. And that's why the log n repetitions is needed. Yeah?
Can you just give kind of order of magnitude numbers for n?
Oh.
What kind of things are you thinking about here?
What to think about? Okay, good.
Yeah.
Not what actually. Yeah, I'm not entirely sure what the actual things in some applications are. But yeah, no. Think of phi as being 10% or something.
10%. N is like what?
I mean, n is huge actually. So one application of this is for monitoring traffic on a network, and you can think of n as being sort of the active IP addresses on some particular network. Right. So suppose one thing, maybe one thing you want to know is like which site is receiving the most packets in any given amount of time, and n would correspond. You know, it could actually correspond to all possible IP addresses, or maybe there's some hashing that you do before this. But n could be very large. I mean, it could be, I don't know, larger. It really depends on the application, but maybe at least like 10 to the 7, 10 to the 8, 10 to 9. I don't know. Yeah. Actually, no. Why not even larger? I mean, 10. I'm not sure. Like, yeah.
And achieving smaller phi is harder, right? I mean, so like.
Yeah.
Late heavy hitters.
Exactly. Yeah. We actually do have nearly optimal dependence on phi too. I'm just going to suppress that for the talk. Okay, so this was the previous best algorithm. It achieves log squared n bits of space. And it turns out that if you allow deletions in the stream, then this log squared is actually optimal in work we showed with Dobal et al. So deletions means, you know, at some point in the stream I can say, please remove one occurrence of I. And you know, this data structure is really easy to maintain in the presence of deletions, right? If I want to remove one occurrence of item 4, I go to its bucket, and instead of adding the sign, I subtract its sign. And log squared is the tight space bound in that case. But what about insertion-only streams? Okay, and this was the model in this paper by Ilan, Matthias, and Segedi, which really sort of revived data streams in theoretical computer science. It has applications in search logs, network traffic, databases, scientific data. The only known lower bound is log n bits. Okay, and this just follows sort of trivially to report the identity of the heavy hitter, of a heavy hitter. Okay, so there's this quadratic gap, and that's our contribution of closing this gap. We give an algorithm using log n bits of space. And recently, we actually removed the log n, so we got log n bits of space. I'll mention that briefly, the log n removal. The same techniques that we use here give a number of other results in data streams. One thing you might want to do is estimate this quantity f2 itself, the sum of squares of frequencies. This is known as the self-join size in databases. It's also the collision probability of a distribution. So it has its own, I mean the second moment is of course important, right? So what we can do is we can estimate it at every single point in the stream. Okay, so at every single point I tell you a constant factor multiplicative approximation to f2. Why is that interesting? Because it's known that at any given time, if I want to estimate f2 with error probability delta, then I need log n times log 1 over delta bits of space. Okay, log n, log 1 over delta with error probability delta at any given time. So the natural thing to do would be to set delta to be 1 over the length of the stream, which is poly n in this case. And that would give you log squared n bits of space for solving this problem. And so we somehow beat that union bound. Okay? And intuitively, we're beating the union bound because F2 is not arbitrary at all points in the stream. It's very related at one time to the next time. Okay. Yeah, so it improves this union bound. Another problem that people look at in practice is just computing the maximum frequency of a data set. Okay? And sort of immediately from our result, we can compute the maximum frequency up to an additive square root epsilon F2. The reason this is immediate is because we just find the heavy hitters and approximate frequencies for those heavy hitters. And we just output the frequency of the largest approximate frequency. And that's our approximation to the largest frequency. Okay, I'm not going to focus on this problem. So in the rest of the talk, I'm going to focus on this algorithm that gets the heavy hitters algorithm.
Is it IIT Kanpur?
Yeah, this was a question in the IIT Kanpur data stream list. Okay, so first, to get some intuition for the problem, yeah, so this is just the statement of the problem. We're assuming phi is constant. Since phi is constant, how many items I can have squared frequency at least phi times F2? Okay, so at most, 10 items can be 10% of F2. So at most order 1 over phi, which is a constant for us. So suppose at the beginning of the algorithm, I just take all my n items and I hash them into a constant number of buckets. Okay, so I just take my n items and I hash some of them here, a constant number of times, and then I run a heavy hitters algorithm on each of these parts of this partition. Okay, so with good probability, all items I whose squared frequency is at least phi times F2 will go to their own bucket. They'll be isolated. Okay, so we just condition on that event, and the problem, the space just blows up by a constant, and the problem reduces to just having a single item I star, which is again between 1 and n, whose frequency is at least square root phi F2, and we're trying to output the value I star, the identity of I star. Okay. So yeah, to get some intuition for this problem, let's make two assumptions that are not quite realistic. We're going to assume that all frequencies of items other than I star are 0 or 1. Okay, just to start. And moreover, even under that assumption, we're going to assume the frequency of I star is at least root n log n. Okay, so note that if all these frequencies are 0, 1, the sum of squared frequencies is at most n. So being a legitimate L2 heavy hitter just means I need to be at least root n. But I'm assuming something stronger, that it's root n log n. Okay. And for the moment, let's also not count the space to store random hash functions. Okay, so we have some huge random tape that we'll deal with later. So the intuition is as follows. Just like in count sketch, we're going to start by assigning each item I a random sign sigma I. And we're going to randomly partition the items now into only 2 buckets. And just like in count sketch, we're going to maintain a signed counter in each bucket. So C1 is the sum over all items I, which hash to bucket 1, h of I equals 1, of sigma I times f sub I. And C2 is the sum over all items I that hash to the second bucket of sigma I times f times I. Same thing as count sketch. And let's suppose that this heavy hitter, I star, hashes to the first bucket. just to see what's happening. Then what do the values C1 and C2 look like as the stream evolves? This is my question. So what do these things look like as you see more and more updates?
It's like square root of n.
Yeah, oh, that's the quantitative bound. I mean, they look like unbiased random walks. Okay? Right? So let's just write these in a little bit of a different way. So we said I star goes to the first bucket. So let's write C1 equals sigma I star f I star plus the sum of all the other items I not equal I star, of their contribution to C1. And let's write C2 in the same way we had on the previous slide. Okay? Then the claim is that C1 minus the sign of I star times f I star and C2, they just evolve as unbiased random walks. Okay, so here we're using our assumption that all the other frequencies were 0 or 1. So we just see an item once, or no times. And we're not counting the space to store the randomness, so all the signs are independent. So when you see a new item, we just see a +1 or a -1 with equal probability. Okay, and what do we know about random walks? As someone in the audience said, we know there's a positive constant c, so that with constant probability, simultaneously at all times in the random walk, the deviation from the origin, the magnitude of the random walk, is at most c root n. Okay, I think this is called Levy's theorem, but it's a standard theorem in random walks. So there's an event that you condition on, and once you condition on that, these counters, well, C1 minus sigma I star f I star and C2 are always bounded by c root n. So this should suggest an algorithm to figure out which bucket contains I star. Okay? Yeah. So here's the algorithm. Eventually, you see at least 2 c root n updates to item I star. Okay, so no matter what sign you assign to I star, by triangle inequality, it means the counter that contains I star is going to be at least larger than c root n. Because the other stuff is at most c root n if this event occurs. But then you know which bucket contains I star. So you sort of learned one bit of information about I star, right? You hash randomly into 2 buckets, you learn a bit of information. Okay, so one thing we could do to recover I star is to repeat this log n times in parallel. If we did this, we'd recover something very similar to the count sketch data structure, right? This would give us log squared n bits of space. We don't want log squared n bits of space, we want close to log n bits of space. So what we can try to do instead is to repeat this log n times sequentially. Okay? So repeating sequentially, so the algorithm is natural. You wait until one of the 2 counters in magnitude exceeds c root n. If it's the first counter, then you say that you say h of I star equals 1, otherwise you say h of I star equals 2. This gives one bit of information about I star. And now you repeat. You just start completely over. Initialize 2 new counters to 0 and perform the procedure again. Okay? You can show, yeah?
The same hash function?
No, new hash functions. Yeah. Yeah, so I'm not keeping track of the randomness, but that's actually a good point because you actually sort of have to keep track of that hash function to sort of recover I star at the end. But let's ignore that for now.
2-level pseudo-random generator or something like that?
Yeah, you can actually de-randomize this part with Nissan pseudo-random generator. But I'll get, if I have time, yeah. Which is kind of like a multi-level, yeah. So if you assume that the frequency of I star is at least root n log n, it takes about root n updates for this to happen once. And you can show that with very good probability, you will have at least, say, 10 log n repetitions for appropriate constants of this hash to 2 bucket process. And you can show that most of them are going to succeed. Okay, sometimes this event doesn't hold for this random walk. And by turn-off bounds, no, these are actually independent. I mean, what you can show is that there's only going to be a single value of I star whose hash values match a 2/3 fraction of the larger side. Okay, so I do this, I see which one's larger, I do it again, I see which one's larger, and by turn-off bounds, I star will be the unique item which matches the larger one on at least a 2/3 fraction. And now I have I star. Or at least now I have all the hash functions which describe I star. Ignoring randomness, I have I star. Okay, so yeah, by the way, so my talk was rescheduled to 4 and the previous speaker was for half an hour, but I don't know how long I can go.
Go until
People leave. Okay, yeah, so it's the last talk. No, okay. Yeah, so, okay. We don't actually have these two assumptions, of course, right? That the frequencies are binary and this heavy thing is super heavy, root n log n instead of just root n. And we're going to fix both of these using the theory of Gaussian processes, okay? So let me say what those are. So a Gaussian process is just a collection of random variables, x sub little t in some capital T is the index set of the random variables. And the only property that you have is that every linear combination of the random variables is Gaussian. In this case, we're only going to be looking at finite collections of random variables. So this word finite doesn't need to be here. Basically, it's a collection of random variables so that any linear combination of these random variables is Gaussian. Okay? Okay. For us, we can, and so in particular, each one of these is Gaussian, though we don't have independence. For us, it's enough to assume the expectation of all the Gaussians, of all the xt's is 0. Okay? That's all from the theory that we're going to need. And you can show in this case, when the expectations are all zeros, the process is entirely determined by the covariances. Okay, the expected value of xs times xt. If I tell you all pairs s and t, I tell you this value. And this is related to a fact that a Gaussian distribution is determined by its mean and covariance. Okay. So for this Gaussian process, we can define a distance function on these indices. So the distance between indices s and t is defined to be the square root of the expected value of xs minus xt squared. Okay? This distance function is actually a metric. It satisfies triangle inequality. It's actually not quite a metric. It's a pseudometric because in general, this can be 0 when s does not equal t. But we don't care about that. We just care that it satisfies the triangle inequality. Okay, so why do we care at all about Gaussian processes? What is the connection to data streams? So suppose we replace the sign sigma I that we've been talking about in these counters. Like we maintain like sigma I, fi. Suppose we replace them with Gaussian random variables g of I. And let's consider sort of just a generic counter c at time t. Time means I've seen t updates in the stream. Then c of t is defined to be the sum over items I of the Gaussian associated with item I, g of I, times the frequency of item I after seeing the first t updates in the stream. Okay, I'm just summing over all items. This is just what a counter might look like. Replacing the signs with Gaussians. Yeah, so FIT is frequency after t insertions. So the claim is that actually C of t is a Gaussian process.
How much information is needed to store the Gaussian?
Yeah, so okay, yeah, so this infinite random tape is getting abused, right? So actually at the end of the day, the Gaussians can be replaced with signs. I just wanted to state it this way for the connection to Gaussian processes. And also at the end of the day, actually 4-wise independence suffices for the Gaussians. But you know, let's ignore that for now. Yeah. So C of t is actually a Gaussian process. Do you guys see why this is true? Right? Suppose I take some finite linear combinations like C of time 1, C of time 2, C of time 3, I add them up. When I add them up, I can group the sum, I can add up the sums that the terms that correspond to the same GI. And then I have a sum of independent GIs. I mean, in the ideal case, all the GIs are independent. And the sum of independent Gaussians is Gaussian, right? So, okay, so it's a Gaussian process. Okay, still, why do we care? So we're going to use actually a very powerful theorem called the chaining inequality, which turns out actually, surprisingly to me, to be sort of exactly what we need here. So the chaining inequality, originally proved by Fernique and but sort of stated in a different language by Talleyrand, is the following. So let x sub t be a Gaussian process, and we're free to choose any nested sequence of subsets of our index set t. Okay, t0 contained in t1, in t2, etc. So that the first set, t0, has size 1, and the ith set, ti, has size at most 2 to the 2 to the I. Then, what the chaining inequality says is the expected value of the maximum absolute value of xt, okay, for all of our random variables xt. The expected maximum value is up to a constant factor, the maximum over indices t of a weighted sum. This weighted sum is the distance of index t to the ith set times 2 to the I over 2 summed over all I.
So the distance from index t to the ith set is just...
Yeah, let me say what that is. This is the natural notion of distance where we saw what the distance between two indices was. Right? It's the square root of the expected value of between index x, s, and index t of xs minus xt squared. That was our distance function associated to this. And the distance between an index t and a set is the minimum over all indices s in the set of the distance between t and s. Okay, so this might be a little bit mysterious, but it'll be, hopefully it'll be clear in a second. So we set our counter, C of t, a generic counter that we might want to maintain in the stream, is a Gaussian process. So what is this thing upper bounding if we apply it to the counter? It's telling you the maximum at any time in the stream of the counter value. Well, that's exactly what we wanted from this random walk theory. Right? The random walks were telling us at any time you never deviate by more than root n, or c root n. This is the same kind of upper bound that random walk theory was giving us before. Now we don't have any assumptions on frequencies being 0 or 1. Okay? So let me just say, okay, so how can we apply this to this counter? So I'm now going to give you a nested sequence of subsets. Okay, I'm going to choose them in a way which makes this right-hand side to be something small that I want. Okay, so let f2 of t be the value of f2, remember the sum of squares of frequencies, after you see t stream updates. And the idea, which I'll show pictorially on the next slide, is to let the Ti be a recursive partitioning of the stream where f2 of t changes roughly by a factor of 2. Okay, so I'm going to show this on the next slide, but I just want to mention that these sets are going to be corresponding to times in the stream at which f2 changes by a certain value. And note that this is not algorithmic, right? I get to specify whatever this is, and this is just going to be a tool in the analysis. Okay. Right, like the expected maximum of this thing, I get to choose whatever I want for my nested sequence of subsets. Okay, so here it is pictorially. So here's my stream. And I'm going to define a sub little t to be the first point in the stream for which the f2 value exceeds half of the overall f2 value, meaning the f2 at the end of the stream divided by 2. There is some unique point when I go through the items in the stream at which the f2 value first exceeds this. And I'm going to set my first set in my nested sequence of subsets to be that index t. In general, what I'm going to do is let capital T sub I be the set of 2 to the 2 to the I times positions in the stream, t1, t2, t2 to the 2 to the I, such that tj is the first time in the stream for which the f2 value at time tj exceeds the overall f2 value times j over 2 to the 2 to the I. Okay, I get to choose 2 to the 2 to the I points, and I evenly spread the f2 value across them. So the conditions we need for applying the chaining inequality hold. We do have a nested sequence of subsets. Okay, these points, as I increases, this is a nested sequence of subsets. The first set has size 1. And by construction, the ith set has size at most 2 to the 2 to the I. Okay, so let's apply the chaining inequality and see what comes out of it. So I've just repeated the statement of the chaining inequality on top here. Yeah, okay, so here's the distance function that Rocco asked about. We need to evaluate this distance for our particular Gaussian process, which is these counters, and for this nested sequence of subsets I just told you. So the distance between t and set t sub I is the minimum over all times tj in t sub I of the distance between t and tj. Okay, which is the square root of the expected value. Now what is our random variable at time t? It's this counter c of t. And what is our random variable at time tj? It's this counter c of tj. So it's the expected value of the squared difference. Okay? But what is c of t minus c of tj? So recall c of t is a counter, right? Like c of t is yeah, it's like the frequencies up to time t times the Gaussian associated with item I. Right? This is c of t. And what is c of tj? It just replaces t with tj. And what is the difference? Well, the difference is exactly the sum with the GIs, but this is replaced with the difference of the frequencies between the two times. Okay. Now, if I take the expected value squared of the differences between two times, I get the f2 value between those two times. But we defined these sets to evenly partition the f2 value across the stream. So there's always, so if I look at time ti, there's always a point tj and ti for which the f2 value between those 2 points is at most f2 over 2 to the 2 to the I. Okay? I mean, that's how we defined this even partitioning.
There's no big jumps in this f2 values as you go along, so the partitioning is fairly even.
The partitioning is fairly even, yeah. Yeah.
The definition wasn't clear to me. I guess this is the grammar maybe, such that tj. I'm just trying to figure out what the j referred to.
tj is the first point in the stream for which
Such that, yeah.
the f2 value at time tj is at least j times f2 of m over 2 to the 2 to the I.
This is really defining two things there. There's a set ti, and there's a value tj.
Oh, yeah. Sorry, so ti is the set of these items.
Explain the day.
Sorry, yeah, this is bad grammar. So ti is the set of these items.
Yeah.
Now, what are these items? tj, which is one item here,
It's a typical element. Okay.
just for some arbitrary j, is the time in the stream for which the f2 value at time tj is at least sort of a j over 2 to the 2 to the I fraction of the overall f2 value. Okay? Yeah. Okay. So you can actually show the, since everything is increasing, the these f2 values in between these blocks, they sum up to at most f2, and they're actually individually at most f2 over 2 to the 2 to the I, which I think was your question. So this value, there's a tj, I can make this at most f2 over 2 to the 2 to the I. Okay, so let's just plug this into the chaining inequality. This says that the expected maximum value of the counter at any time is up to a constant factor, the max over all times of this weighted sum. This weighted sum is the sum over all I of 2 to the I over 2 times this distance. This distance we just said is at most f2 over 2 to the 2 to the I square root. So that decays faster than geometric. That's order square root f2. We didn't actually need the full power of the chaining, actually. Anything that made this geometric would have been enough for us.
It's a little magical, so how do you get rid of the Gaussians?
Yeah, so so just replacing Gaussians with plus minus ones. Actually, the chaining inequality holds. Yeah, so you can show that like the expected supremum with plus minus ones, and that for Gaussians, the one for plus minus ones is upper bounded by the one for Gaussians up to a constant factor. Okay, so this is called the comparison theorem, I think. So this has the same behavior as for random walks, right? Because it says, in our random walk example, this order square root of f2 would have been square root of n. And this is saying at no time do we deviate more from the origin than square root of n. But this is a much more general statement in terms of f2. Okay? Okay. Okay, so yeah, we have some assumptions that we wanted to remove with this earlier intuition. One was that all the frequencies were binary, and one was that even if they are, this heavy guy is root n log n. And what we just showed, this Gaussian process, this chaining inequality theory, it removes the restriction that the frequencies are binary. Nowhere did we use that in the argument. Okay. Yeah, so just to reiterate, the random walk bound of c root n holds without this restriction in that earlier example. But we sort of still need fi star to be at least, sorry, this should be root f2 log n. And why was that? Because we said, okay, well, we're going to wait a little bit until one of these counters exceeds c root f2, or c root n in the earlier example. And when it does, we learn one bit of information about I star. And then we repeat, we do it again. That's kind of why we needed log n, this log n here. because we needed it to be sufficiently frequent so that we could do this thing log n times to get log n bits of information about the heavy hitter. But ideally we'd like to just replace this restriction with f of I star is at least square root phi f2, the legitimate heavy hitter. Okay, so I'm going to ignore log n factors for this talk. I'll just give a simple way of achieving this. And what we can do is we can assume that fi star is at least log n times square root of f2. Okay, I can assume fi star is at least log n times square root of f2. Why is that? Well, we said in the beginning we can hash to a number of buckets and run our algorithm on each bucket. Okay, run our heavy hitters algorithm on each of the buckets independently. So instead of hashing to a constant number of buckets at the beginning of the stream, suppose I hash into log n buckets. That'll blow up my space by a log n factor, but it'll make my thing my true heavy hitter even heavier. Okay, because what's left in the bucket is only likely to be a 1 over log n fraction of the overall sum of squared frequencies. Okay, so this is a way of making your item sort of artificially larger. Now we could hash to log n buckets, then we would use too much space. But let's hash to log n buckets. Okay. So now, this is the final technical slide on the algorithm. Okay, so we know our item is squared frequency is log n times the sum of the squares of all the other frequencies. Let's do the following procedure, which we call amplification. We're going to create log n pairs of streams from the input stream. Okay, so we have our input stream, and we're going to create a left stream and a right stream. What that means, and we're going to do that, that's going to partition the stream. We're going to partition the stream into two pieces. Some items go to a left stream, and the remaining items go to a right stream. And we're going to do that again and again. And we're going to do that log n times independently. So just to formally state what this is, for each j in your log n repetitions of this process, you choose a hash function h sub j, which maps the items 1 through n to either the left, call it 0, or the right, call it 1. And the jth stream, the left part, is the original stream restricted to items I, which hash to 0.
The hashing is based on the value, not on the index. So this is a hashing from one
from items, yeah. It's not based on, all the updates are like +1 or something. Yeah, it's based on the item identifier. So half of the, roughly. So some fraction of the items go to the left and some go to the right, defined by this hash function. Okay. Yeah, so the ones that go to the left say the hash function evaluated on the ID is 0, and to the right is the remaining items that hash to 1. Okay, now we're going to maintain a counter for the left stream and for the right stream. Yeah, I'm sort of over time, so if you want to leave, go ahead. Sort of the main ideas have been presented, but I'm just going to finish this since we're almost done. Yeah, so we have a left stream and a right stream, and we're going to maintain a counter for the left stream and a counter for the right stream. And the counter is just the inner product with Gaussians and the frequencies of the items that go to the left stream. And the counter on the right is just the inner product of Gaussians and the frequencies with the items that go to the right stream. These generic counters that we've been looking at. So by applying this chaining inequality and a turn-off bound, okay, let me just say something. The I star is going to go either to the left or the right stream. And the side that it goes to is likely to be much larger than the other side. Why? Because all of these things, they're about root f2 in expectation at all times by this chaining inequality. But we said I star was log n times larger than square root of f2. So it's much larger. It's like log n times the noise in everything that's left. Now that square root of f2 though, that bound was only an expectation for the noisy stuff. But we have log n repetitions of this. And so by Markov bound, all of these things will be at most square root of f2 times log n. On all repetitions for the left and the right, these counter values by the chaining inequality and the Markov bound will be at most square root of f2 log n. But I star is larger than square root of f2 log n. So what's going to happen after I see enough updates in the stream? The larger counter is going to be the one that contains I star. Okay? And I'm doing this log n times independently. And the larger counter stays larger forever by the chaining inequality. Right? At all times, this is at most root f2 log n, the remaining stuff. So after I see enough updates of my heavy item, then it's always going to be larger than the remaining stuff. And so the larger counter stays larger forever. Okay? So the larger counter is the one that contains I star. Now what was the point of this? Well, the point of this is, suppose we just run our algorithm of learning one bit of I star, and then learning another bit of I star, like hash into 2 buckets, learn a bit of I star, hash into 2 buckets, learn a bit of I star. But we only run it on the items that correspond to being in the bucket which has the larger counter on all log n repetitions. Right? So we have 2 counters for the first repetition, 2 counters for the next one, 2 counters for the next one. After I see enough updates, this counter is always going to be larger. Then this counter is always going to be larger. This counter is always going to be larger. And now I'm just going to run this process of learning one bit of I star only on the items that hash to the larger counter in all log n repetitions. Okay, so I'm basically sieving, like I'm filtering out the stream. I'm only looking at those items which go to the larger counter in all the repetitions. I star goes there, so we still have our heavy hitter. And the expected amount of other stuff that goes there, that's the point. Like the f2 value of all the other stuff that agrees with all the larger counters, well, it's going to be roughly f2 over polylog n. Right? Like, what's the fraction of items that agrees in all log n repetitions? 1 over 2 to the log n. That's roughly 1 over log n. I can make that 1 over log squared n if I want. And their expected f2 value is f2 over polylog n. Well, that's great, because I star goes there. And now all these items that also go there got even smaller. So now I'm like super heavy. I'm not just log n times what's left. I'm polylog n times what's left. Does that make sense? So this is why we call it amplification. But if I'm polylog n times what's left, then I just have what I had before. Right? I learn one bit, then I learn another bit, and I can repeat that log n times, because I'm so much heavier than what's left. So that's the...
That's like the sequential repetition then?
Yeah, the sequential repetition thing. Yeah, so there is like something here, which is those, the larger of the 2 counters, it is changing early in the stream, like which counter is larger. Like it's changing, and whenever it changes, I do have to restart my whole procedure of learning one bit of I star. But after I see enough updates, it never changes. The larger one stays larger forever.
Sorry, so you're doing this in parallel with sort of guessing which is a subset of candidates.
So you're going to lose your session share. Keep going.
Oh, okay, yeah, sorry. Yeah, so you're doing this, and every time the larger counter changes, you restart this learn one bit at a time procedure. But you know, after enough times in this, after a long enough time in the stream, the larger counter stays larger forever, and you have enough updates at that point to actually learn I star. Okay, so is it clear, or as clear as can be? Okay, so that's sort of the amplification. Yeah, so this is I'm really out of time. De-randomization, we have to account for the randomness in our algorithm. There are 2 things. We need to de-randomize the Gaussian process. We need to de-randomize the hash functions that were used to learn a bit of information. We achieve one, let me just say some keywords without any details, by using a de-randomized Johnson-Lindenstrass theorem. So roughly speaking, we take these, this inner product of Gaussians with these frequencies. we first take this n-dimensional frequency vector and we squash it down to a log n-dimensional frequency vector using Johnson-Lindenstrauss. And that preserves all the pairwise distances, expected value fi minus fj squared. That's sort of what Johnson-Lindenstrauss does. And if you do that, there's this thing called Slepian's lemma, which says if you preserve the distance function at all pairs by a constant, then you also, the Gaussian process is roughly preserved. So the supremum is preserved. 2 is using a more standard technique called Nissan pseudorandom generator and streaming pioneered by Indic. And let me just mention that we recently removed the log n and got log n bits. There were multiple sources where the log n was coming from. One was this amplification that I just discussed. And here we use a key observation, which is that as you're doing this filtering of items, the heavy item is becoming even heavier as you go. So if I instead of having log n, if I only have like a constant number, then my item is, I filter out a constant fraction. My item is already becoming a little bit heavier. And this allows you to sort of bootstrap and save that log n. Another thing is with the derandomization, we show 4-wise independence is enough to derandomize our particular Gaussian process. And just to conclude, so we beat count sketch for L2 heavy hitters. We get log n bits ultimately instead of log squared n bits. And some new results for estimating F2 at all times in a stream and maximum frequency estimation. A lot of questions here. So count sketch is used in practice for things like network monitoring that I said. And we have a preliminary implementation. And it's not clear yet if it's a significant practical improvement, but we're trying to make it one. And sort of like Gaussian processes are new to data streams. And so maybe they're helpful for solving other problems more generally. So that's all. Thanks. Any questions?
So it's a Gaussian process. So can you do this for norms, so moments other than the second moment, 0 to 2, like the index stable distribution?
Oh, the index stable stuff. Yeah, so I think the F2, the L2 guarantee, so it actually implies the L1 guarantee for constant phi and epsilon. And so I think it implies the LP guarantee for constant phi and epsilon for any p between 0 and 2. The issue, though, is for p larger than 2, you actually can't achieve polylogarithmic space. It's known that you need polynomial in n, like n to the omega 1 space. Yeah.
Is there an intuition for that? Why is that?
The intuition for that? Yeah, so.
Different between 2 and 3.
Yeah, it's a good question. So there's a communication complexity-based proof. The intuition is sort of like the concentration that you get in L2 is sort of the best kind of concentration you can get for random variables. I mean, this is sort of I mean, sort of the hard instance is, yeah, if you have a frequency which is like n to the 1/3, and all the frequencies are 1, you'd want to find this with L3 heavy hitters. And sort of, you can take linear combinations of your frequencies, but sort of the standard deviation for whatever, I mean, you're going to choose some random variables here. And for sort of many classes of random variables, this is going to concentrate to roughly plus or minus root n, which is going to be larger than this. And there's sort of no family of random variables that really helps you to find this item. That's some intuition as to why this upper bound would fail. Yeah, I don't know if that helps. Or I can explain the lower bound proof if you're interested, maybe after the, yeah. Any other questions? Okay, so thanks.